This is Chapter 7, Assignment, Problem 7. I'll give you a moment to read it. You can pause this while you read the problem. The first question is, show the sampling distribution of p-bar to 4 decimal places. Now, they already tell you that the population proportion that drink bottled water more than once a week is 0.34. So this is the expected value for p-bar or the sampling distribution of p-bar. It's simply the expected value, which is 0.34. No need to have it to 4 decimal places. The next part of the problem is sigma sub p-bar, which some people refer to as the standard deviation of p-bar, but it's also referred to as the standard error of p-bar, the sampling proportion. To solve the standard deviation or the standard error for p-bar, I switched to the statistical toolkit because what we want to find is the standard deviation of the sample proportion. In this situation, we don't know the population size, so I'm using the normal probability tool for the sample population proportion of infinite population or where the population size is not given. They do tell you the sample size. If you recall, the sample size was 540. So we use the tool, 540, the mean population proportion, or the expected value for the population proportion, 0.34. So that gives us a 0.02039 as our standard deviation of the sample proportion. We were asked to round this to 4 decimal places, so that rounds to 0.0204. Next, based on this 540 in the sample, we want to know the probability that the sample proportion will be within 0.07 of the population proportion. And again, they want this to 4 decimal places. So if we go plus or minus 0.07 from our mean proportion, that upper limit is going to be 0.41. The lower limit will be 0.27. So I'm going to enter in the proportion of interest for the upper limit. So the probability of having less than 0.41 is 0.9997. If I were to then subtract the probability of being less than 0.27 to 0.0003, gives me a probability of that interval being 0.9994. Even if the sample size changes, the expected population proportion does not change. However, the standard error will change based on a smaller sample size. As I said, the population proportion, the mean proportion, will not change with a smaller sample size. The standard error, however, will change. And because I'm going to switch to my spreadsheet tool, we'll also see that the probability within that interval will change as well. So back with the tool, we've changed the sample size to 280. The mean population proportion is still the same. The standard deviation of that sample proportion, also called the standard error, will be different, 0.0283 to 4 decimal places. I've gone on and entered in the upper limit for that interval, that is symmetrical about the mean of the proportion. So what we have is 0.9933. If we subtract the proportion in the upper tail, 0.0067, the probability of the proportion falling within that interval is 0.9866. Part E is a bit difficult because of the wording as measured by an increase in probability. How much do you gain in precision by taking a larger sample in parts A and B rather than a smaller sample in C and D? Now you would think, and all you're doing is taking the difference between this 0.9994 and 0.9866. You would consider that to be an increase in precision, which is what the second box indicates. But for some reason, the correct answer that they mark here is reduced by. The precision isn't reduced by taking a larger sample, it's actually increased by taking a larger sample. So this wording is somewhat confusing.